All right, so we're back again here with another problem. This is the maximum length of pair chain problem. Actually, let me check something. Did we do this properly? I don't know if we. I don't know if I got my other video up here on the stream. YouTube streaming is kind of tricky. Yeah, we got it. Okay. Yeah, I was gonna say. Want to make sure the other video uploaded. Okay, so here we are. 20 seconds in. All right, maximum, yeah. So I quickly checked this problem just to make sure, because someone had asked, hey, can you please do this in Java? So I wanted to make sure it was actually a Java problem. The other problem was also Java problem, but wasn't really, it was kind of, not really much of an algorithm question. Somewhat of a data structure question, but still relatively easy to just use another data structure. All right, maximum length of pair chain. Given an array of n pairs, where pairs of I is equal to left sub I, right sub I, and left sub I is less than right sub I. After a pair, P2, CD follows a pair P1 equals AB if B is less than C. CD follows AB if B is less than C. Okay, interesting. So they're sort of like sorted from there. These are actually like intervals, I guess. Inclusive, I guess maybe, are they inclusive? They might be inclusive. They're intervals. They're intervals, and we're saying that another interval follows the previous interval if, C is less than D and A is less than B, but also B is less than C. A chain of pairs can be formed in this fashion. Turn the length longest chain which can be formed. You do not need to use all the given intervals. You can select pairs in any order. Oh, that's interesting. Okay, this is a nifty question. So this is a good one. Let's think about this. So I guess my thoughts or my thinking for this one would be also. Let me see. Is our volume okay? I'm kind of yelling. Kind of talking loudly. Let me lower the volume a bit. Hopefully it's okay. Like I lowered the volume a bit. Hopefully that's fine. Let me know if it should be louder or not. Okay, I don't immediately have an answer. This kind of makes me think of a topological sort for some reason. That's like kind of my first thoughts. Those are my first thoughts. Let's see. Okay, int pairs 1, 2, 2, 3, 3, 4, 2. Longest chain is 1, 2 to 3, 4. All right, they need to be strictly less than, so not less than or equal to, but strictly less than also. Pairs 1, 2, 7, 8, 4, 5. So 1, 2, 4, 5, and 7, 8 is the longest chain. All right, output 3. So I think sorting this is probably the best thing to do. Okay, sir. Thank you. Appreciate that. Thank you, Ganesh. All right. So yes, my thinking is sorting left to right. Just basically sort, and you can actually sort on the x coordinates first. Call them x and y coordinates. So x coordinates left side, right side's y coordinate. I think you sort on the x coordinates and then do a secondary sort on the right coordinates. And actually in Java you can use a stable sort. Not Java. C++. I wonder if Java has a stable sort. Let me see something here. Because there's a thing you can do with a stable sort that's kind of nifty. Raise sort. Guaranteed to be stable. Nice. All right. There's something I wanted to show. I don't want to show that, but something I wanted to show with stable sort that you can use. Something interesting. Okay. So we want to sort on the x values and then sort on the y values, and the idea is that we want to use the smallest of any of these. Now my thinking is, well, this is an interesting question. So like I said, I don't actually know the answer. I'm thinking sorting helps, so let's sort first. And then, because we don't have too many numbers to work with, like we only have 1,000 numbers that we're even looking at in the first place, so it's not, sorting won't be too expensive. So we sort first, then we want to say, we want, of the values that we could pick next, we want the one that has the smallest y value first, and then all of the intersecting intervals So actually another way to express this is we are looking for the largest subset of non-intersecting intervals. I've actually solved this problem a few times before now. Yeah, I've seen this a few times. I've solved it a few times. I'm pretty sure you can do it in just a sort, and then there's like an algorithm you can use to select your intervals. But what you're going to do is, so this actually, yeah, this question's been shown on LeetCode quite a few times with quite a few different variations. Like I've actually seen this a few times as sort of a duplicate. Actually, I should have looked at the discussion for the other problem, but whatever, that's fine. We don't need to go back. Yeah, I've actually solved this before. I'm thinking about it now. I'm realizing I think I know what this is, and I've solved it before. So it's the largest subset of intervals that don't overlap. Yeah, that's pretty much what we're looking at here. Now the question is, this could be kind of tricky because let's say you do have, like, in these examples, the first pair you do want to pick in every case, right? But let's say you don't want to pick the first pair. Is it possible that you pick the first pair and it actually ends up excluding a lot of other, sort of overshadowing a lot of other intervals? In that case, you actually don't want necessarily the first one. So yeah, you're actually looking to, so I wouldn't say I've solved this problem. I've solved a similar problem, a related problem, a problem where you wanted to maximize, I think, the overlapping that you can get, something like that. But here you want to minimize overlapping as much as you can. Interesting. So I think actually in this case you'd want to sort by the, you might actually want to sort by the second coordinate first, because well, I mean, I don't know. There are a few ways to look at this, I guess. This also makes me think of what they call the longest increasing subsequence problem. The longest increasing subsequence is basically if you have a list of numbers and you want to find the, of all the subsequences, you want increasing, or it could be monotonically increasing, or non-decreasing, it could be non-decreasing subsequences also. But of all the possible subsequences of a set of a sequence of numbers, you want the one that's the longest, where all the numbers in that subsequence are increasing. There's like a nifty way to solve that problem. That's clever, and I think you could apply it to this one. You could do the longest increasing subsequence of the rightmost values, but not quite though, because, well, it's kind of like just the longest increasing subsequence period, maybe. Yeah, I guess you could. I guess you could sort this left to right first, as mentioned, but then also you could perform a longest increasing subsequence algorithm on this, in that, like, the sequence of, like, what's the rightmost value of, yeah, the minimum rightmost value of the subsequence of non-overlapping intervals that have one interval, two intervals, three intervals, etc. Right? And if you always keep track of the smallest rightmost value, then each time you can update that whole array that you have with oh, that's interesting. So then you can update that array each time with the next interval you're considering, and if you can improve sort of the next spot with a better rightmost value, I suppose, then you should, right? And what's interesting about that is you can do a binary search to find that spot too, because the only intervals that you can, only sets of intervals, subsets, subsequence of intervals that you can improve would be the ones that have a smaller rightmost value already. You have the added challenge of which of these can you improve? I don't know if you can do this in n-log n time. Actually, this might be quadratic time. With only 1,000, it's not too bad. You can maybe do it in quadratic time is not too bad, but I don't know if you can do this in linear time. Problem statement is not clear. No, the problem statement is clear. I get it. The problem statement is clear. I understand what they're asking, but the solution is challenging. What they're saying is no, I get it. I get it. What they're saying is you're given like a set of intervals, like a timeline of a whole bunch of different intervals, and they want to know what's the largest non-overlapping subset of these intervals, where they all are not overlapping with each other. It's actually pretty simple problem, but to express. But the solution is not clear at all. I mean, the solution is challenging. Like I said, I want to say longest increasing subsequence is probably some variation of that would solve this. But how do we do that? What do we do? Let's see. I think about this. Sorry. Thinking, pondering here. Sorry. I have a lot of thoughts that come into my mind from time to time that I just don't really want, and it's frustrating. All right, focus. We're looking, right, so the longest increasing subsequence solution I don't think necessarily works. And the reason is, even if we do a binary search to find the next interval that could be improved based on the y coordinates, the problem, when we're considering this interval that we're gonna, this next interval to consider, is that it doesn't have, the x coordinates are an issue. So actually the x coordinate needs to be past the y coordinate. That's what needs to be. And now also another issue is, does this improve the other possibilities? The new x coordinate needs to be past. It gets a little, it's a little more wonky to try that, because with the longest increasing subsequence problem, every integer is just a single integer. Like, we're not dealing with pairs of integers. Whereas when you update your interval, I guess you update the previous interval, you actually change two numbers rather than one. And it's not obvious how that affects sort of the rest of the algorithm. I guess I'm also not sure if you necessarily need to sort things first either. Not sure if that even really matters. I think it does. I think you do want to do that. So that way you can guarantee you're always looking at the closest x values first, furthest to the left x values. What you're trying to optimize for would be, I want to say it's the rightmost values. Yeah. So in other words, selecting interval 1, 4 wouldn't be as good as 2, 3, even though 1, 4 has a smaller x value, it has that larger y value on the right side. So yeah, but you wouldn't be able to emplace 2, 3. Like, yeah, in other words, you use x to search for where you could place. So if you have the y values or what's exposed, you can place as long as the x value is to the right of the y value, but then you get a new y value, and you want to check that against the next the next y value. It's also hard to describe this without drawing it. Basically, you have an array that keeps track of the minimum y values, and this array, it's going to be at the first value is going to say, okay, this is the minimum y value we can get of all possible subsets of intervals that only have one non-overlapping interval. The next value would be the smallest possible y value we can get of all possible subsets of intervals where we have two non-overlapping intervals, and the next is for 3, the next is for 4, etc. And the idea is that when you consider an interval, you can do a binary search to find out which of these selections could actually even have this interval. It's even possible, right? And of those that are possible, so those will be all the ones that have a y value that is smaller. Now, naturally, this entire array should be sorted, right? It's going to ultimately be sorted because basically the smallest possible subset of size sort of n-1 is necessarily going to be, first it's going to be smaller than the subset with n, and it's going to have it's further to the right, to the left. So all the intervals are further to the left than the n case. And in theory, the n case would be built off of the n-1 case, right? It would sort of, you'd add another interval to that. But it's possible later that you find a way to update that interval with something better, like a smaller number. I think that's why I want to sort things, is so that way. Yeah, what's interesting is that these. There's no order we need to select the pairs in, though. That's kind of tripping me up quite a bit. Yeah, the longest increasing subsequence, you can't just reorder. Like, if you could just reorder in the longest increasing subsequence, then actually you could just sort the elements and that's it, and you're done. It's not really the longest increasing subsequence anymore. So actually, this is maybe my mistake. It's not really. You don't need to use the longest increasing subsequence. You can actually just sort these intervals. But then the issue is, like, you need to have the non-overlapping sequence of intervals. So maybe this is a much easier than I thought. Like, this might be easier than I'm making it out to be. I don't know. I'm trying to like connect it to a problem I've already seen before. If we sort these intervals, this is a good question, man. This is a good question. The largest non-overlapping subset. Largest size non-overlapping subset. Excuse me. Well, a solution that would be correct but not very efficient would be you can just check every possible subset and check whether it's overlapping. And then every possible subset, whether or not they're overlapping, of the non-overlapping subsets, you can count their sizes and then just take the largest of all those sizes. You can do it that way. That's one approach. Not a particularly good approach, but one approach. I think actually the way you would do this is you would iterate through your subsets, but then eliminate things that are not possible more quickly or efficiently. So you select one, and I think sorting this is the best thing to do. Start with sorting. Select an interval, and then I guess if you intersect with something else, then you kind of branch into two possibilities where, well, that's what I was getting at before, where I think it's best to actually just keep the minimum sort of y coordinate in an array. So of all the possible choices you can have for the first interval, you should pick the one that has the smallest y value, and then I think it's just always true, right? I think it's necessarily the case that the length of the longest chain must include the first. Yeah, I think that'll necessarily include that interval. So I guess we sort by y values then first. And then the longest chain then you have intervals, some certain number of intervals that have an x value that's to the right, and then I guess of all the x values that are to the right of that first y value, you want to pick the one that also has the smallest y value. Yeah, that's sort of optimal. It's tricky. Yeah. I don't know, man. It's hard. It's like I'm kind of like struggling to think it through, because I think I'm making this harder than it is. Yeah, because if the elements were not minimal in the y value, then you can only make things harder for yourself as you progress through the algorithm. So I guess I think it's just a greedy algorithm is what you need. I think that's it. I think it's that simple. Sorting helps, but I'm having a hard time proving it, I guess, in my mind. How are we doing on time? Yeah, 20 minutes. We've thought about this already. I don't want to say I've solved this already. That's not true. That's actually not true. I've solved similar problems or related problems, but I haven't solved this one. There is such a thing as also using an interval tree, but I'm not really sure. Yeah, an interval tree, but I'm not sure if we need an interval tree for this. I don't think so. Yeah, I don't think that's the case at all. Not necessarily. Well, actually, could say something like non-overlapping pieces, like breaking up the intervals into non-overlapping chunks, like a divide and conquer kind of an algorithm. So you could do like the left half of the intervals that don't overlap and the right half of the intervals that don't overlap, and then the large, if you recursively found the largest on the left half and the largest on the right half, and then you have found a way to combine those two. Since you split on some value, I guess, somewhere, then necessarily the left and the right halves don't intersect with each other. I don't know about that. That's another thing to think about, a consideration. Again, sorting these intervals. Excuse me. Left to right. But they definitely overlap with each other. They definitely do intersect somewhere. I guess you would need to sort them. No, I don't know. I don't even know how you would divide and conquer, really. That's a little weird. The merging part is definitely strange. I mean, even if you could solve on the left side and solve on the right side, but how do you even define left and right? I guess you'd have to say, like, you know, half of the intervals after sorting using a stable sort on X and Y. Yeah, half of the intervals would be sort of one subproblem, the other half the other subproblem, but then combining the two results is not necessarily the most efficient way, or not the most obvious thing, especially because they definitely overlap somewhere. They definitely could overlap if you define it that way. I don't know, man. Struggling, not sure of the answer. You can do, you definitely can. Well, I want to say I was on the right track with, like, trying to minimize the y values, the rightmost values as you go. I think that's correct. I think that makes sense, because if you don't pick the, let's suppose we don't pick the interval with the first interval that we pick on our returned list. Let's say we don't pick the interval with the smallest rightmost value, or smallest y value. Then we could replace what we did pick with that value and potentially get a better answer. And you can do that for any interval that's possible. Yeah, although you run into an issue where, because that's only true for the first element, because the left side is somewhat unbounded. Like, your x value could be as far to the left as you want for the first interval. But for the second interval, yeah, you'd want to minimize the y value on the first interval, so that way you have more options for your second interval to select from, because that's limited by the x value. And that could only improve your selections if you have the ability to select a better better interval. And again, you'd want to pick the minimum y value for two intervals that are not overlapping, the minimum y possible, because again, it gives you the best options for the next step. So I think that's inductively true, that you would always want to have whatever subsequence of intervals you're considering the n subsets, you'd want to take of the n minus 1 subsets, you'd want to have the minimum y value, which then gives us our structure that we had before, where we were saying, okay, well, let's have like a list of these, 1 to n minus 1 possible arrangements of intervals, or possible subsequence of intervals, and also let's have in all those spots up to this point the ones with the smallest y value. And then we can search through using our x value, we can search through which of these it's even possible to add this next interval. And then we can do that in logarithmic time per interval. But the problem with that is, yeah, we can try to append now. I think the tricky thing with doing that is, what happens to everything below, right? Like let's say we're doing something like that, and we have some intervals, like 1, 2, 3, 4, 5. We have different subsets of intervals, and then we find some x value that's relatively small, I guess. Like let's say we update something somewhere in the middle, right? We find we consider this new interval, and we update right in the middle. I guess that's why I want to sort ahead of time. That's the thing I'm kind of hung up on. Yeah, I think that's why I want to sort ahead of time, because it kind of eliminates that possibility, but not necessarily. Like I'm just thinking, like let's say we get an interval that's a really small interval, but it's kind of somewhere in the middle, and we somehow end up updating, some part of our array. What about all the elements that follow that, right? So we say, there's n minus 1 and n, and we want to say, okay, we have this new interval. It's actually better than the n minus 1 case, so it had a better y value. So it's probably a smaller interval that's slightly to the right. So it has a larger x value, but a smaller y value, right? So it improves our previous possibility. So we improve it, but then all of the things that followed that improvement, all of those things would need to be updated too. I think that's the challenging part that I'm kind of struggling with. Is like, it's a little bit different than the longest increasing subsequence, because we can select these intervals in any order we want to or need to select them in. I think that's what I'm struggling with. Whereas the longest increasing subsequence, you can't. So you don't really have the same problem. Yeah, I see that. Interesting. So why? I mean, maybe it's that simple. Maybe it's super greedy. Like you just sort on x and y. So you want the smallest x and the smallest y. I guess maybe you could do smallest y and then smallest x. You could sort by y and then sort by x, and then you just have just a straight greedy select left to right, minimizing on the y value. So if you see, I don't know, man, that seems so, I don't know. I think this is probably a lot easier than I'm making it out to be, but I'm just kind of struggling to think about it. All right, we've been like over 30 minutes just kind of pondering it. Oof. This is a challenging question, man. It's a challenging question. Intervals. Questions about intervals are always kind of annoying, because intervals are kind of tricky to work with. Maybe I can. No, it's no point in really writing things down. You can, but it's like not really necessary. If you don't really know the answer, you don't really know the answer. And you got to really sit and think about it for a while. Excuse me. You can perform a kind of depth first search as well, but I don't think that's particularly good either. Like, select an interval and then see, what other intervals you can select after that, kind of a thing. But I don't really like that either. I think that's kind of poor approach. I think it's inefficient, unnecessarily inefficient. Yeah. Basically, that's pretty much going through all the different possible subsets or subsequences. But you don't need to go through all of them, I think. I think that's almost certainly the case. This makes me think also of like a topological sort kind of a thing. Where you're looking for the longest chain in a topological sort. Maybe that's another way of looking at this or thinking about this. Actually, I think that's what I should be doing. I'm sorry. I think that's what I should have done from the beginning. I kind of thought this might be a topological sort, but actually, yeah, this is a topological sort. So each interval could be a node in the graph, and one node, quote unquote, follows another node, so it's topologically sorted to the right of another node. If we have sort of left and right sorting, it follows. Yeah, there's an edge in the DAG if this is the case, if sort of if B is less than C, then there's an edge from P1 to P2. Yeah, I think that's the way to think about it. The tricky thing about this though is that there are, I guess, a lot of edges in the DAG. That's a transitive property that we have there. So it's a topological sort with a transitive property. So I think that's what I probably should have came up with first, is start with a topological sort, finding the longest path in a topological sort. Now, it's not even a no. Oh, it's confusing. I don't know, man. This is tricky. I don't know if I can. We should read the discussion afterwards. This is a tricky question. I think you can translate this to a graph problem as described, right? But the problem with that is that if you make a graph out of this, there's 1,000 intervals, but then it could be, because you have like the edge set could be quadratic, right? So then you could be in a situation where you're looking for the longest path in the DAG, right? I guess the greatest depth of the tree of any path. Yeah, you're looking for the longest path in the tree. You can also make this an undirected graph too, I guess technically, because the interval with the smallest y value, I think, should be the root. Would be you can make it a DAG and make that the root. But the problem with that is, yeah, you're looking for the longest. No, you could do this linearly. You could do it in linear time, I think. Yeah, I guess that's why you sort. Yeah, okay. This is a little confusing. I think you do it n log n time. You're gonna make a tree structure out of this. It's not a tree structure. It's not a DAG either. It's actually a. It's a DAG. Sorry, it's not a tree. It's a DAG. You're gonna make a DAG. You're going to make a DAG. And you're gonna do this recursively. And each recursive step, you're gonna find the longest path to the leaves from any particular node. That's what we're gonna do, sort of recursively. And you take, of all of the children, you're going to take the minimum path, and then, or excuse me, the maximum, the longest path, the largest path, and then you add 1 for this parent node, and then you return at the end. And all of the children that you can recurse on, you don't return to any child. So this is actually kind of how a topological sort works too. It's very similar. You don't return to, you mark the node. Once you visited that node, you don't return to it. after you've found the largest path from this node to the end. And yeah, that's very interesting. So you use a little bit of like memoization, we'll call it. We'll use a hash map for this. So if you have a key, if you have a key in the hash map, then you just return that. Okay, I think I got it. I think I got an idea. It's kind of interesting, but it's, yeah, this shouldn't have taken me so long. Also, I think, yeah, it shouldn't have taken so long, but that's all right. So, I actually think this is still quadratic. Even, yeah, even after all of that thinking, I think this is still quadratic time, which is not very efficient. The reason why I think it's quadratic is I don't think you can do better than the size of the edge set, even if you have transitive. Like you're trying to avoid jumping over, basically trying to avoid the transitive steps that you might take. And the issue there is at each node you're going to have to at least consider all of the other nodes that could be children. Like in order to figure out which children to even look at, you have to at least look at all of the other children. But the problem is that, like, yeah, even if those children you've already visited them, you still have to check that you visited them. So you still need to go through all of those pairs that are to the right. That's very tricky. That is a tricky thing. Huh. I don't know, man. I don't know how to do this more efficiently than that. I mean, I have an idea, but it's not good. No, man. I mean, you can do it with 1,000. It's fine. It works. It's doable. But maybe so I have to admit there is a problem that I have from time to time where I see a problem and I think like, oh, I can do this more efficiently than expected, or try to, and you end up wasting a lot of time just like kind of smacking your head at this problem, trying to figure out like, how can I do this more efficiently when it's not actually possible to do it more efficiently, or they're not expecting you to do it that efficiently. Yeah, that's awkward. So I think the way to do this, what we're gonna do is we're going to use we're not going to use a hash map. It's not really necessary. Excuse me. We're going to use an array of n values, where each array represents the longest chain starting from a particular pair. And what's going to happen is we can iterate over all of the other pairs that aren't that pair, and if they are, if any of those pairs follow the one we're looking at, then we'll recurse on that pair, and if not, then we don't consider it. So that's basically, yeah, so basically we are going to perform like a graph search, more or less. We're gonna perform a graph search. That's pretty much what this is coming down to. We're gonna just we're gonna memoize using an array though instead of a hash map. We don't really need to use a hash map, but yeah, we're just gonna use a depth first search. It's just a depth first search. That's it. Super simple depth first search. Done. That's all. That's all. All right, so we want a subroutine. So we can say, so we're gonna use a lambda expression, and it's gonna be, like A follows B. A follows B, or pair follows pair. Pair A follows pair B. let's do that. So we want this Boolean. Now there is I think there is a functional interface. Like we can actually just have like a private interface here, and just have a function defined, which is, you know, pair A follows pair B, and this is a Boolean, and it takes int pair A, int pair B, and these could be integers, I think. Well, that's fine. And then we want to say this actually isn't defined, right? It's abstract. And then we could say this interface is not anonymous, but we're just going to say, I don't know what you would call this, like binary predicate. Something like this. And then now we can say, you know, binary pred B is equal to, now we can use the lambda expression, the lambda expression syntax in Java. So we have int pair A, or A and B, we could say. And now we just say, I think Java you can do like const A, B, or X, Y, we'll say. Or let's do A, B, C, D, I want to say, but we could do X and Y is better, or A1, or P1, P2 is probably better. And then I want to say something like A, B, I don't know if I can do it this way, but something like const integer AB is equal to P1, and then a similar thing for, if this isn't the right syntax, let's do structured binding in Java. Let's take a look. You can do structured binding in C++, but how do you do? Awkward hack, arrays, empty. Oh, that's weird. Don't recommend this. Neither shorter nor easier to understand. Oh, I don't know. That's awkward. Okay. So I guess we're not going to use structured binding. I don't know. Okay. All right. 0. I guess you just do this. I don't know. Oops. I don't know if P was the best symbol to pick for that. It's something like this that we want, and then we would say return as A, B, C, D. We want B less than C. I think that's simple. Binary predicate. I think the functional interface has a binary predicate. So we don't actually need, we could just we don't need to write our own interface. Excuse me. Yeah, by function. By predicate is what we want. Java util function. So really we want import java.util.function, and I guess it would be everything there. I don't know. Something like this. And then we don't really need this anymore. We can use the generic, so we can use by predicate of int. Oops. I don't know if generics allow you to do that though. Can we do this? Just pair check. Something like this. Hold on. Does this compile? So that's lambda expression syntax. It does compile. Okay, that's interesting. Nice. All right, so you can use generics. So we don't actually don't need to have our own interface there. All right. So we can use an array list of integers. We'll call it memoize. We're going to memoize with that. And we're going to let this be, we actually want an array even. It's even better to use an array. I don't recall if it's length or size. I think it's length for arrays in Java. So, and we're also going to fill this to, I think you can do fill, it's arrays.fill, so fill with -1, right? Let's see. Yeah. Oh. Huh. Excuse me. I am wrong. That's only, yeah, it doesn't work the way that I thought it would. There we go. That's what we want. Okay. And we're going to write a recursive function. Can we write a recursive lambda function? Is that a thing in in Java? Is that even possible? I actually don't think you do recursive lambdas in Java. I think it's a little too complicated. We'll just call it a helper. Well, you can do, oh dude. This is gonna get really complicated if we try to do, let's just write a helper. It's fine. It's okay. Yeah, that's fine. We can pass the memo as a reference to the helper. That's fine. All right, call it DFS helper. Yeah, I think it's a little too complicated. All right, and we're gonna return an integer, I think. Memo. We want our pairs, but now we don't have access to our predicate anymore, though. That's kind of annoying. Lambda expression. I guess you could just give it the predicate as an argument. Hopefully this works. call it BP pair check. All right, so we have our predicate, reference to our predicate. We have a reference to our pairs, our memo, memoization, our basically our hash function. Oh, you know what we don't have? Oh, that's awkward. Yeah. Well, we can actually use the index of the pair as the entry to the memoization map. I think actually that's fine. We don't need to sort first. I don't think we need that either, by the way. So we can do. Maybe I do need a little more practice in Java. There's some just like awkward things here and there that I just am not super practiced in. So there is no base case, I think. Well, okay. There's base cases and there's a recursive case. So the recursive case, we're going to take all the other pairs except for the index. I'd say current index is probably better. All the other pairs except for the current index that are also, where BP is also true if you compare these two pairs to each other, right? The pair at the current index versus all the other pairs. For all those where BP is true, you're going to recurse, but you're going to take the largest of all those values, and you're going to return 1 plus that. And yeah. Yeah. And I guess the return value would initially just be 0. And so just 1 plus 0 if there are no children. So I think there really isn't a base case. The only base case you have is the memoization. So we say if memo of current index is not equal to -1, then you return memo of current index. And we're going to say int ret equals 0. Loop over all of the pairs dot length plus I is not equal to current index. Right, not including the current index. Then we'll say int other pair. It's going to be pairs of I. If BP, no, it's BP dot call, I think is what the interface has for by predicate. Test. Okay, we use test. There's a few. And or negate, default. Interesting. Test is what we want. Okay. And we want to say current pairs of I, test current pair against other pair. If that's true, then we're going to say value is going to be DFS helper of current index now is I, and pairs is the same, memo is the same, BP is the same. And we're going to update ret is if ret is less than value, then update ret equal to value. And then we return ret plus 1. I think it's that simple. DFS over the children, over the pairs that follow. Given pair, 1 plus the largest, the chains. Something like this. Excuse me. Oh, one more detail. We're going to say memo of current index is then equal to ret plus 1, and then return ret plus 1. Okay, I think it's that simple. So we've already visited this node, then we'll return immediately. Something as simple as that. I think that's what we want. And we start on, we do actually want to find the right node to begin on for this to work properly. Current index, pairs, memo, pp. Let's go. Pairs, memo, yeah, pairs, memo, pair check. And then the one thing we need here is which index do we start on? Now the index we start on is going to be the interval with the, find the interval with the leftmost second value, all of the intervals. And the way we do that is there like a minimum routine in Java? Could use a comparator. Collections. Let's see. Min collection extends object and comparable. Yeah, Java wildcards is still something I kind of need to study a little bit more, quite frankly. Turns the minimum element of the given collection according to the natural ordering of its elements. So we actually want you to use a comparator. Order induced by the specified comparator. So we're going to use an anonymous comparator that we're going to build in order to get the minimum pair that we're looking for. Now, what's tricky about this is we don't want the pair itself. Actually, we want the index of that pair. So that's very awkward. We're actually not going to use we're going to write our own routine then. Yeah, that's very awkward. We want the index of the minimum. So unfortunately, we can't even use the generics here for that. I think it's not going to work. But that's interesting. You can do something like that. Index of the interval. The smallest second value. Okay. So we'll do that. Ret will be 0, and we're going to say for, I guess it'll be like, can you do it this way? I don't know if you can. I guess you got to do int I equals 0, I is less than or I equals 1. We can do I is less than pairs.length. So we're going to use just a raw for loop here. And we're going to say pairs. So we're going to say int a equals pairs of I. No, we'll do int p equals pairs of I. And then we'll say if P of 1 is less than pairs of ret of 1. And ret equals I. Something like that. And then, and not ret, it's going to be target index or initial index. This is kind of ugly. It's kind of ugly, not ideal, not the best. Find symbol, current pair, pairs of I, variable I. 18. Excuse me. Excuse me. Excuse me. Oh, it worked. Hey. Compiled and executed. Imagine that. Wow. Wow. Huh. Let's go for it. I don't know if it's right. I have no idea. I feel like I need to use more test cases. Oh, it worked. Okay. Hey. How long did that take? Only an hour. Only an hour. Wow. That is nice. I don't know, man. Not the most efficient way to do this, I think. Let's see what the discussion has to say. I didn't really like this one. Yeah, we converted it to just a graph question. Also, pretty awkward the way that I programmed it too. Overall, it took me a while. It took me a long time. The answer's not very efficient, and it's kind of ugly, the code. Everything about this I dislike how I approached it. It's okay, I guess. Yeah, it's kind of, well, if I decided on this answer sooner, it would have been a lot faster to code. I mean, it really only took a few minutes to code this, I think. Maybe 20, 30 minutes. I shouldn't say a few minutes. 20, 30 minutes to code it, but I really was hesitating for a while on like how I wanted to actually approach the problem. And some raw loops in here is not great. Glad that it works though. At least we got that far. We should look at the discussion to see why we're not so fast. Slam to function. Let's see. Greedy, bottom up, DP, top down. Okay, interesting. 3 solutions, same as 435, non-overlapping intervals. Ooh. I did solve this already. I thought I did. O of log n log n, greedy solution. Rust, O of n squared, some. Nice, super simple, longest increasing subsequence solution. You know, I thought maybe that'd be the case. I don't know, man. Variation of the longest increasing subsequence, one line change. Yeah, man, I don't know. Alright, sure. They said it was easy. Alright, it took me a while. I didn't get it. Didn't get those. You should want to go for the most votes. Those are usually the best. Proof the greedy solution. 4-liner Python greedy. I'm annoyed. Java and login. Let's look at that one. Clean code. Earliest deadline, first algorithm, greedy, same as maximum jobs we can accomplish. Very simple DP. Very simple DP without DP. I'm annoyed in using a max priority queue. Binary search easy to understand. I didn't get it. I don't know, man. I thought this was. It looked recognized. It looked like something I've seen before. I was kind of struggling. It was taking me too long. It was taking me too long, man. I didn't see it. I didn't see it. I'm upset though. I'm annoyed. I'm annoyed. Let's see. Array.sort pairs AB A1 minus B1. Equivalent to interval scheduling problem, we sort the array by finishing time. Choose the first one, discard all those that conflict. Continue this process until the end. And log in. Whoa. 2 assumptions after sorting. Oh yeah, the sorting is what actually causes it to be unlog in. I guess it's linear after this. You know, I'm so annoyed. I had already solved something like this. I'd already done this. Alright. Okay. Okay. Interval scheduling problem. Sort the array by finishing time. Choose the first one. Discard all those that conflict. Continue this process until the end. But why is it linear? Or nlog n? Wow. That's pretty good. That's pretty good. That's what I was saying before. I was like, I think it's just super simple greedy algorithm. Like you just sort it and go, and you're on your way. I couldn't prove it. You know, it's kind of stuck on that. I don't know. It's just such a like you can prove it if you think about it for a while, but like you kind of got to think about it for some time. Got to get it right. Oh man, dude, I'm annoyed. I'm annoyed. I'm annoyed. Interval questions. All right, where's my sorry, just give me a second here. My glasses are slowly, like, I've had them for a few years now, and they're kind of slowly, I guess, breaking down. I don't know. They're getting like scratches and things on them now, where it used to be I could clean my glasses and I could see fine after that, but now they're sort of just slowly accumulating scratches and things and all kinds of stuff on it. Yeah, man. Well, I mean, we got it, but not as we should have, right? We didn't do a good job on this one. That's all right. That's why we practice. That's why we practice. Okay. Interval scheduling problem. Sort the array by finishing time. Choose the first one. Interesting. I'm going to use that. Choose the first one, discard all those that conflict, and continue this process until the end. Choose the first one, sort the arrays by finishing time. Choose the first one, discard all those that conflict, and continue this process until the end. Alright, so while I is less than n, increment the count. Current end is pairs of I 1. Sure. I starts off at 0. While I is less than n, and pairs of I 0 is less than current end, increment I. The ones that conflict, oh, right, I see. Well, I is less than n, and these are the ones that conflict, you just skip them. But you're also, you actually don't even care, you only care about the ending time. You actually don't even really care about the start time of the pair. Oh, I see. Okay, that's why. So you just pick the first one that has an ending time that's sort of the next ending time, and then all the ones that, okay, I see. Wow, so super simple greedy algorithm, like really, really simple. Okay. Dude, I couldn't do it. I couldn't handle it. I couldn't handle it. I was trying to figure it out. I was like, I'm pretty sure you could do a greedy algorithm, but I couldn't think of how to prove that. Like, how do you prove that this is correct? That's the question, right? Like proving that this is correct. Okay. Okay, so the algorithm is as follows, right? You sort by the ending time, and then you're going to pick the first element, the smallest ending time, start with that, and then pick the next element that has the next smallest ending time, and disregard all of the intervals that conflict, all the intervals that intersect, right? The intervals that are not, what do you call that? The intervals that are not, I guess just discard all those that conflict is a simple way to express it, but any interval, discard the intervals that are not, there's another way to say it though, disjoint, disjoint, discard the disjoint interval, discard the non-disjoint intervals, or keep only, find the next disjoint interval that is, the smallest disjoint interval, find the next disjoint interval with the smallest ending value. That's ending time. That's exactly how to express it, right? So find the next smallest, the next interval, the next disjoint interval with this, find the next disjoint interval with the smallest ending time. That's the greedy algorithm. Recurse, and then just keep repeating, not recurse, but keep iterating. Each time finding the smallest, the disjoint interval with the smallest ending time. That's actually the way to describe this algorithm. It's super simple if you think of it that way. So, but why is it correct though? That's the question. Well, I think what you would prove, you'd have to prove that that I guess the inductive hypothesis is that you have up to this point. So there's n and n minus 1. So the tricky thing is let's say n is the value of the largest subsequence of these intervals that are disjointed subintervals. The largest subset of disjoint intervals. The largest subset of disjoint intervals from the set of intervals. And we want to prove that the algorithm that we just described will ultimately yield that subset. And I want to say if we follow this algorithm up to the n minus 1 subset, then it's necessarily the case that adding the next disjoint subset, the next disjoint interval will result in what we're looking for. However, if we don't minimize, so it could be that if we don't minimize our ending value for the n minus 1. So I think the way to prove it is that at each step we'll end up with a sequence of n, or just say k, let's say k less than n. We'll end up with a sequence of k disjoint intervals. And the only way so taking the smallest possible ending time of all the possible disjoint intervals we could select will guarantee the greatest number of options possible in the future of the algorithm, I guess. And so you must select the greatest possible number of options in order to get the greatest sized subset. So that's a very awkward way of saying it, but it's partially the reason it's true, but it's also doesn't really follow. It's also something of a non sequitur. I think that's why I was struggling so much. But that's kind of what I was getting at before. I was trying to describe that, but it's kind of hard to say it, to articulate that. Let's try again. Let's keep trying. How do we articulate this? Why is it true? Let's prove that it's true, right? Let's prove it. We think it's true. I think it is true, but why? Suppose that we didn't select the best ending time, right? For the n-1 option. Then it's possible that we wouldn't be able to use the next disjoint set that's required to get the maximum. That's just in the last two steps though. Like we need something stronger, like stronger proof. Why is it true though? How do you prove that it's true? Ah. Oh no. Well, I think the way you'd argue it at each step. So at each step, the following is true: that if you consider the largest subsequence, right, or subset of disjoint intervals. If we take any particular k step in the algorithm where we have, I guess we could split this subset into two pieces. There's sort of the left side and the right side, where there's k elements on the left side, and we'll call it alpha minus k, where alpha is the largest, the size of the largest set. So there's k on the left side and alpha minus k on the right side. If we did not take or actually let's even do it this way. We'll say there's the kth disjoint set that we're considering. We have k minus 1 on the left side, the kth disjoint set, and alpha minus k minus 1 on the right side, right? So that's in every inductive step. That's what we're looking at. If we suppose that we could actually, in theory, we could take any of the, for k could be any of the elements found on the right side, and k could be any of the elements found on the right side which have a larger schedule, a larger ending time. And if we took any of those, it would exclude k, so we would not get the maximum alpha at the end. So we can't take any of those. But if we take any, suppose we took any, we could take, clearly we can't take any conflicting sets for k that conflict with the left side. That just won't work. But we also we have a choice of any of the non-conflicting intervals that are disjoint, right? But optimally, we would want the smallest ending time, because it's possible to preclude possible intervals later on in the algorithm. I mean, vaguely that's why it's correct, but you could prove at least that any other choice won't be as greedy, basically. But that's such a hard thing to prove correctly though. Like that necessarily gives you the answer you're looking for, because it's possible you won't get the right answer, but it's not. You don't necessarily need to take the smallest every time, which is a tricky thing too. It's not always the case. It's just that it will be it gives you that gives you the best possible. But actually, it's not unique, the answer to this question. So, but it is guaranteed that you will get, of these solutions, you will get one of the maximal solution. So yeah, it's not unique. So there are maximal solutions. So it's not, but so you really just need to prove that you're going to get one of the maximal solutions. You're guaranteed to get one of the maximal solutions. I guess you could say you can sort of do this inductively and suppose that you took, if you were to consider, so you can consider any possible pair initially. Let's say that way. Let's do it that way. So you take any possible pair initially, and in order to get the solution we're looking for, you want to select that pair in such a way that two things happen. One, there is a set of non-conflicting intervals, whatever's left, like whatever's of all the intervals left. I'm gonna sneeze here. Oh man, I'm struggling here. I am struggling because I guess you could say like something like you can build, as long as you, of all the pairs possible, you would select a disjoint pair, a disjoint interval, right? So you have some set of intervals already, and you select a disjoint interval. I want to say like, yeah, you want to get like an inductive step going here somehow, that you could prove that, suppose you already had some disjoint intervals, and if you take the last ending time of those disjoint intervals, that will filter out all of the other disjoint intervals. Excuse me, all the impossible intervals, right? That's true. That's obviously true, right? That's gives you an efficient way to do that. No matter what you have already accumulated. And then if you were to take the next smallest schedule time from the set of intervals that don't conflict, yeah, of the disjoint, the remaining disjoint intervals, possible disjoint intervals, that gives you your best chances. I don't know how to like rigorously explain that though, or prove that. Like, I don't know. Okay, how do they explain it? How do they explain it? Let's see somebody else's explanation. I should be able to explain it, but I'm really struggling to explain it. That's kind of more important, because if you can explain that quickly and efficiently, you can come up with the like proof for the greedy algorithm. Then you can just write the greedy algorithm and you're done. Like you can get through this really quickly. Like obviously this is a very efficient, very easy to code this, right? Excuse me. Key to understanding the greedy algorithm is understand two assumptions. After sorting, longest chain must contain pairs of 0. Suppose it doesn't. That is, suppose the longest chain C starts at pairs k for some k greater than 0. We obviously have pairs of k1 is greater than equal to pairs of 0, 1 due to sorting. You can always form a new chain C prime by replacing pairs of k with pairs of 0, whose length would be no shorter than C, obviously. We just have to prove C prime to be also a chain without overlapping. This is trivial. Pairs of Z ends no later than pairs of k. And if you can lead a chain with pairs of k, you can also lead to a chain with pairs of 0 without introducing new overlapping. Right, so I got, yeah, that one I got. I got that far. Tie situations do not matter. You do not have to specify how to sort the pairs when the ends are at a tie. Consider such an example: 1, 2, 1, 4, 3, 4. We start at 1, 2, and 1, 4 is skipped. And then we add 3, 4 if we have instead 1, 2, 3, 4, 1, 4. Then we start at 1, 2. And then we add 3, 4, and we skip 1, 4. In the two different situations, the pair 1, 4, that is the pair that is tied but has a smaller start, is skipped anyway, albeit by different eyes. You can directly try to prove the statement when there are intervals with tying ends. Optimal solution will never choose one with smaller start over the other one which has a relatively larger start. This is intuitive. Same end, smaller start means longer, more overlapping. Why bother? think the algorithm strategy then justifies itself in the light of these two assumptions and needs no further proof. Hope this helps. Kind of, not exactly. Prove by exchange. C be the pair chain of the maximum length, CP be the pth pair in C. Suppose there is a pair Q such that Q is greater than CP minus 1, 1, and Q1 is less than or equal to CP1. Place CP with Q, resulting pair chain will not be shorter than the original C, therefore we can do such replacement as many as we want. I don't know if that actually proves this though. I don't really know about that. Space should be linear because of array sort. Oh. Oof. Oof. Problem is almost the same. Only difference is that the border touching is not considered as overlap 435. Pretty sure I solved 435 already. Pretty sure I solved 435 already. But I solved it differently. This is actually, it's not linear O of n. It's interesting he said it's O of n because of array sort. It's actually not true. This is not using extra space, O of n extra space. Or actually, if this is in place, this could, yeah, actually maybe it could be. If this is in place, then it's not O of n, but if it's not in place, it might not be in place. I don't know how they implemented array sort in Java. See if anybody responded to this. Oh, it is merge sort. Okay, there you go. I wasn't sure. Very interesting solution. Also, this is back in 2020. That's not one space then if you're using merge sort in Java. Oh, excuse me. I have to think about it again. So yeah, no man, that's a classic question. But I don't know. Yeah, I don't know why. Like, arguing for the solution is really tricky. Obviously, if I knew it, I would have immediately argued it. I don't know, man. I don't know what to say. Shoot. All right, let's go back to the problem and think about it again. So, okay. I use a depth first search. Not the best way, but good enough given that we only have 1,000 elements to work through. All right, we'll give this an upvote too because this is a kind of a classic question. This is something that I think a lot of programmers kind of should just know the answer to. At this point, like I would basically just memorize the answer for this one, but let's think about it. So why does the greedy algorithm, let's prove the correctness of the greedy algorithm. Let's start with that. So we have the algorithm already, because what you can do is like, you can think up different possible algorithms that might work. However, if you can prove that it's correct, then you're done and you can code it and you can move on. So you can kind of guess at different algorithms or just think up different algorithms you've seen that might work. I was trying to think up actually divide and conquer algorithm, but that didn't really make a lot of sense, or it didn't really quite work the way I would have liked it to. Yeah, let's think about this some more. Let's like, how do we prove this really quickly that it's correct? Like, how do we prove that's correct at all? Let's start with that. Because now I'm going to use this algorithm probably every time I see a question like this. But how do we prove it? This is also really interesting because it does provide, as I was describing, it does provide an interesting solution for DAG questions that have, like, you can generalize this solution to like a whole set of problems, like DAG questions where the relational property is transitive. So any DAG question where the relational property is transitive, if you're looking for the largest, basically the longest sequence of values of nodes, longest I guess sequence of nodes, or the longest path, the longest path through the DAG, then you can use a similar approach. Now, problem with that though is that you would need, you're basically, in this case, you're optimizing on one of the parameters that's given, the ending time of the intervals, but that you may not be able to do that actually in all cases, so I take that back. You may not be able to generalize a greedy approach, but it is interesting. Why is this right? Like, how do we prove that this is right? Well, what someone else was suggesting was right. You could prove it if you have a maximal solution. Take any other interval that has a smaller start time, as long as it doesn't conflict with the, if you took any maximal interval solution and you were to sort that maximal solution on the n times, then given any, like, let's say the kth index of the kth disjoint set or disjoint interval, kth interval in that solution, if you could replace that with any interval that has the same ending time, as long as the starting time doesn't conflict with the k-1 element's ending time. Right, and that also guarantees that it doesn't conflict with any of the other k element, k-2 elements, and also doesn't conflict with any of the k+1, all the elements that are to the right of k+1 have an index greater than k+1. So, or the first k-2 elements, right. So yeah, that's true. So that shows you that the maximal length solutions are not unique. But how do you prove that you're always going to get a maximal? What did we just do? How do you prove that we're not going to get that we're always going to get a maximal solution using this algorithm? How do you prove the truth of a greedy algorithm? So let's consider all of the maximal solutions, and let's remove the last element, right? So we're looking for, so the maximal solutions have, like, let's say n is, every maximal solution, consider the case where you have n, right, consider all the maximal solutions that have size, and let n be the size of any maximal solution. Now we want an algorithm that'll get us to n-1. In that case, well, I guess by inductive hypothesis we can say assume we have an algorithm already that gets us the n-1 case, right? In that regard, that means we're going to get to any of the solutions that don't include. Now there's a lot of ways we can get there though, because these intervals it's not necessarily, like, we just need one other disjoint set in order to get from n-1 to n. So there are a lot of different possible ways we could have gotten to n-1, and we just need to select one more nth value. So I don't know if this is like the right way to try to prove this. I want to say it's not always the case, no matter what. No, that approach is not going to work. What I'm just describing. How about? Well, obviously we can prove if the element with the smallest ending time is going to be part of the maximal solution. That we could prove, right? Because if you took an element with a larger ending time, then yeah, I guess it's really tricky. I guess let's consider our maximal solutions and consider them sorted by the end time. Like that, I think that's the thing I'm really tripping over, because it's like I don't know, man. I don't know. Proving is so hard. I don't know why it's so hard, but it just seems so difficult. This is something, by the way, that you're gonna, when you're like applying for jobs and things, and they interview, they may ask you to think about these things. They may ask you to prove why the thing you think is right, why it's right. I'm gonna lay down, man. This is making my head hurt trying to think about this. They actually, nobody that I read so far, I don't think any of them gave like a really solid proof. So even the first part where you said, okay, the ending, the interval with the smallest ending time is going to be present in a maximal solution. That's not, the proof of that's not necessarily true, because, well, I guess you have to be careful how you prove it, I suppose. Suppose it's not included. There we go. That's maybe the way to go. Suppose that you have a maximal. Yeah. You could do it that way. Okay. Suppose you have a maximal solution. Suppose that you did not include the ending time, the interval with the smallest ending time. If you did not include it, then you can swap that. If it is truly maximal, then you can always swap that value with whatever element you have that has the smallest ending time, because it'll be guaranteed to be to the left of that or equal, and all the other disjoint elements must be disjoint, right? They'll all be to the right. They will all be to the right of that element you just added. So you could. So actually, it doesn't necessarily need to be in the maximal solution, but it could be in the maximal solution. So I think that's true for every element in the. Yeah, I think you would argue it that way. So you would say you can take the first element in the maximal solution could be the interval with if you were to sort of sort your intervals in the maximal solution. Or actually, yeah, you could say, because the maximal solution isn't necessarily sorted, right? I mean, it's just a set of intervals, so it's just kind of like a hodgepodge of intervals, I guess. In the maximal solution, you can always include the interval with the smallest ending time, and then you can argue if you were to sort each element in the see, that doesn't make a lot that doesn't actually give us our solution, though. That doesn't. I guess what I want to say is that the result, we want to prove that the result of our algorithm will be a maximal solution. So first things first, definitely the algorithm, it's clear from the algorithm that all of these elements will be disjoint from each other. So we do have some amount of disjoint intervals at the end of our algorithm's execution. That's clear, right? That should be obvious, because we have a set of, so initially we have, actually before and after, the invariant before and after each iteration is that we have a subset of disjoint intervals, and then we either add one or we finish the algorithm, right? Add another disjoint one subset, or we finish the algorithm. So yeah, we know that we're going to have some number of disjoint intervals. and there'll be at least one, right? Size at least one. Now, excuse me. How do we prove that the number of disjoint intervals at the end of the algorithm is a maximal number of possible disjoint intervals? Yeah, that's what we want to prove. And I guess the way you would prove that is, suppose that it was not maximal. That means that there was some other interval that we could have considered to insert into the result of our algorithm, right? Maybe we do it that way. So there's some interval that we could still insert. The question would be, where can we insert that interval, right? If we show that we could not insert that interval anywhere, or actually, I think what we would want to show is that that interval is either already in the set, our disjoint sets, or it could not be inserted. And if we prove that that's the case, then that implies that our result is maximal, that there is no more disjoint intervals that can be added. So no, that's not really correct. No, that's not really correct, because yeah, it doesn't make sense either. Because you could have a result that you can't add any more disjoint sets to, but it's not a maximal number. It's just that how you selected those sets. You just selected them inefficiently. Like yeah, you could select it in such a way where you can add more sets, but it also isn't a maximal number of sets. So that's not really correct either. The correct way to prove this. How do we even prove it? It says I'm struggling so much. We want to prove that the result of our algorithm has a number of disjoint sets that are disjoint from each other, and the number of those sets is equal to the maximal number of possible disjoint sets for any subset selection you can pick of disjoint subsets of the intervals. That's a mouthful, but yeah, we want to show that those two numbers are equal to each other. That of the maximal possible, that this algorithm gives us at least one subset that has that maximal number. Gives us one subset. Yeah, gives us one subset that has that maximal number. Proving that it's disjoint is easy. We got that. That's fine. But proving that it's maximal, that's not possible to arrange your intervals in such a way where you get more than that. That's what it means to be maximal. It's actually not. It's not saying that we can't add another disjoint set. It's that. Well, I mean, it is and it isn't. We're saying that there's not another way to arrange your intervals such that we can get at least one more set included. Yeah. So let's suppose that there was another way to arrange these intervals such that we could fit another set. What I want to say is that if that's the case, then this set, well, basically I want to say, like, yeah, we want to prove that that's not possible. I want to prove it's not possible. How and get a contradiction somewhere. If suppose there was another arrangement. Yeah, okay, let's do it this way. Suppose that there was another arrangement of sets that would give you one more than the result of what our algorithm would give you, right? So our algorithm doesn't give us a maximal set, and there's some other arrangement that exists. Okay. In order for that to be the case, there could be quite a few differences actually between these sets, right? I mean, they could be you could totally select different sets altogether, different elements altogether. I guess what I want to argue is that let's do it this. Let's prove it this way. I have a better way of trying to prove this. Let's consider of all the possible ending times that you can get, right? So for any disjoint set, there is a largest ending time. There's a final ending time, right? And let's consider at each possible ending time what the maximal number of sets could be for each particular ending time, right? So there's like a set of ending times that are possible, and let's sort that set, right, from left to right. So there's a set of ending times left to right, and each of those ending times, there's only so many intervals that have a smaller ending time, right? So we can kind of, this is sort of like a breaking the problem down to the subproblems, right? And it's necessarily the case that if we considered the maximal number of sets that have maximal number of subsets. So if we consider it's a mouthful. Consider the subsets that have a maximal number of arrangements with a maximal number of sets that where all of the intervals are smaller than that, or less than or equal to that particular end time, right? If we consider for each end time basically the subproblem, we can take a subset of the intervals given a particular end time where all of those intervals are less than or equal to that particular end time. All of their values are less than or equal to that particular end time. Let's do it that way. So if we do that, then we know that the solution of this question on each of those subsets will produce a a non-decreasing sequence from left to right over the end times necessarily, because because if we increase the end time, then the subset of intervals that are available to us to choose from only will increase, and that implies that whatever the solution was, the optimal arrangement for a smaller end time is available to us for the larger end time, and we might even be able to fit a few more intervals in there, right? So I think that's the argument, actually. I think that's sufficient, because that implies that if that's the case, then you'd want to optimize over the end times, over the interval end times. That you would want to So knowing that that's a non-decreasing subsequence or non-decreasing sequence, right? Showing that's a non-decreasing sequence. I think that's clear, right? Without even having any algorithm to calculate those values, we just know that that's true. How does that help us though? Like, what does that do for us? Why do we want to show that? I think that means that implies that a greedy algorithm is correct, something like that. How does that relate to our algorithm? Let's do it that way. How does that relate to our algorithm? Why does that possibly show that our algorithm is correct? Because suppose then that we did have an algorithm to find. So if we took all these end times, these possible end times, and we had some algorithm that we knew was going to be correct. So by inductive hypothesis, for some end time, we'll call it the kth end time, we had the correct arrangement, right, for it to be optimal. If we now consider that some other end time that's larger, it's like k plus 1 end time. I guess there could be some sequence of end times that we might want to consider. But let's take the next end time such that we could fit one more element, right? So that would be that there's some arrangement that we have, and we want the next end time that gives us one more. So we increase to the next best arrangement, right? Well, that end time would necessarily be the end time of an element that so yeah, okay. So this is interesting. That next best end time must have the following properties, right? Let's take all the sets that have the same optimal configuration amount, the same number of sets for this kth end time that we selected. And let's take for that kth end time, let's say that there's some maximal x arrangement. Let's consider all the arrangements that have a smaller end time but still have x intervals. So we're going to minimize, right? We're actually going to take, instead of the kth end time, we're going to take some, I'll call it alpha, that's smaller than k, that the smallest that end time that does also have the same x for the arrangement, right? So we minimize on that end time there. And then now we say, okay, we also want the smallest end time that has x plus 1, the smallest end time such that we have x plus 1 intervals. Because we can minimize, right? We can absolutely minimize on our kth end time, so find some alpha end time, index alpha end time. And then also we can then say that implies that the smallest next end time that has x plus 1, so yeah, the next end time that has x plus 1 elements, intervals in the arrangement, if at all, right, if it exists at all, we're assuming that we can add at least one. That must be the alpha, the smallest end time configuration for alpha, plus some interval with plus the next disjoint interval that is smaller, that has the smallest end time of all possible disjoint intervals, which is exactly what our algorithm is suggesting, right? That's exactly what our algorithm adds. So then we can add that, and then we know that that is the absolute smallest end time that we can get that has x plus 1 intervals rather than x intervals, right? And that, again, that's exactly what our algorithm does. Our algorithm at each step, presumably, assuming we can prove that at each step, not only is our algorithm at that alpha end time, but also that the next smallest possible configuration end time of all possible configurations would be exactly what we just described. Would be exactly the next step. And I think that gives us an inductive proof at that point. That gives us our inductive proof. And assuming also that there is another possible configuration, because it is possible that all of the other intervals after that point conflict. That we have an optimal configuration, but all of the other possible intervals at that point conflict, and so then that is actually at that point you have the maximal for the entire subset. I guess as part of our construction, there is a certain end time that we reach where we include the entire subset, all of the intervals, all of the sets in the interval. We've already considered all of them, and then we're done at that point. And again, there is actually an alpha end time there for of all those possible configurations that has the minimal end time, while still having a maximal number of intervals altogether. So yeah, that's a very confusing and roundabout way of explaining it. Let me see if I can kind of shorten that. So I think the way to prove it is to consider subsets of the intervals such that all of the intervals in that subset have end times less than or equal to a particular end time. And then now what you can show is that of all the possible end times to consider, if we take algorithms, any algorithm, if we took a perfect algorithm, a correct algorithm, and applied it to the subset of intervals that are less than or equal to that particular end time, then we would get some maximal values for each of those end times, and we can show that that's a non-decreasing sequence. And the reason it's non-decreasing is that you can always fit, if you increase your end time, you would only get more options to add to your disjoint intervals. So I think that's intuitive. Not just intuitive, but I think it's clear. I think I think you don't need to explain that further, right? It's that if you add, that's a non-decreasing sequence because you can only have better rearrangements with more options. So I think that's clear. And then because of that, that implies that if there is a better arrangement that exists for some larger end time, so given some kth end time or ith end time, and what the optimal configuration is, one optimal configuration for that end time, there are two things to consider. That if there is a end time, larger end time that has a greater, let's say has one more element. Let's do it that way. There is another end time that has one more element has one more element in its optimal configuration, optimal selection. Then you can it's necessarily the case that the end time, I think what do you say, kth? Yeah. If we consider the kth end time, there is some alpha end time that's less than or equal to the kth end time, such that alpha end time also has the same maximal number. I think that's also necessarily the case. Obviously the case. It might just be itself, or it could be a smaller number. So let's consider that alpha end time that's minimal for the given optimal configuration value. And then we know in order to go from the alpha, which has x total elements, let's call that x total elements, to a configuration that has x plus 1 elements, there must be some, it's necessarily the case that the end time that we're going to use is exactly the end time of any of the intervals, of all the disjoint intervals. It's going to be that are not already included in our optimal configuration, that are disjoint from our optimal configuration, optimal selection rather. So it's disjoint from our optimal selection, and they're just end of those. It must be the one with the smallest end time. But by definition, right? Because if you picked any of the other ones that were larger, then that wouldn't be the next end time. That wouldn't actually be the next minimum end time. That would be an end time that might be one of the next possible end times, but it would be larger than the one that we could pick, this minimal one. So in order to get that next minimal end time, we would actually pick the minimal end time that we have already looked at, and then add exactly that interval to get that next minimal end time. And by induction, since we've already have, since on so we picked our minimum configuration, and then also by adding exactly that interval, we know that we are at exactly the next minimum interval. Excuse me, the next minimum configuration, next minimum end time. And I think that's it. I think that actually gives us the inductive step. I think that gives us the inductive step. And then we can just prove that obviously the minimum end time of one non-disjoint interval is trivially just the interval with the smallest end time of all of the intervals. Okay, that proves that this algorithm works. That's a very complicated and long-winded explanation, but that's basically why. Interesting. Not something I would have come up with in 5 minutes. I don't think so. No, I really had to like sit and ponder that for a while. So forgive me for having such a long-winded explanation. Also forgive me for, taking so much time to solve this problem. But so we solved it using a DFS. So technically would have been able to solve it in an interview, although it would have taken me a very long time. But the actual proof is actually kind of hard to express. It's kind of complicated, kind of hard to express. But the basic idea is pretty simple. And then actually solving this is relatively easy. So I'm actually going to copy what he used because I like what he did. We're going to pairs, and we're going to use a lambda expression, and actually you can leave out different pieces, so you can do, it's the end time. So the way he did this is you actually it's a three-way comparison, and you just subtract the second. So b of 1 minus a of 1 to give you, this is sort by the end times. That's really interesting. I kind of don't have like a lot of practice or experience with Java's sorting routines, so like this is something that I wouldn't have thought of. But if you do it this way, what'll happen is if you're looking at, you're going to compare A and B. A is less than B if you return a negative number for your three-way comparison. They're equal if you return a 0. And so I think you do A1 minus B1. So if you do that, and then you just system.out.println. Let's do pairs of 0. I don't know what this is going to print, by the way. This won't compile. Interesting. So output 0. Okay, what? Oh, standard out 2. Yeah, okay. If we did it the other way around, we would get 4 here, I think. Yeah. So if A is less than B, you get a negative number, right? Because if you do A minus B, yeah, that's what you want. So basically, vaguely, the sorting kind of work. You could subtract the two values as your comparator, and that'll sort in ascending from. Yeah. Okay, makes sense. Fair enough. Okay, so now we're pretty much going to write the same routine that was written before, almost exactly the same thing. So we have, int count is what he used. It's pretty much going to be like the same. I don't know how else to write it. I don't know how else to write it. Current maybe. I think he just used I. And they said there's always going to be at least 1, so we can initialize this at 1 and say current is equal to 0, right? The first pair always. And then end time would be pairs of 0, 1. And we can say it's really a for loop where increment current and current is less than pairs.length. And you would say not just current, but also the count. Yeah, that's fine. Another for loop. So you would say, as long as the pairs of the current pair, if that it's end, as long as the end time is less than current end time. I think I'm doing this wrong. And really just increment this each time. Same thing. As long as current is less than pairs.length, and this pair is then you can increment current. It's actually the other way around. You would that's kind of confusing. What you're gonna do is you're gonna update the end time. And you're gonna increment the count. The problem though, so really it's actually all of the ones that are, that's kind of confusing. I'm doing this wrong. I'm trying to be clever here. It's probably not a good idea. You're going to toss out all the pairs. Oh, I'm sorry. It's actually, yeah. So we should use a while loop actually. This is, yeah, we really should just use while loops. I think it's too confusing to not use a while loop. Try to use a for loop. You could use a for loop, but we'll just go with a while loop. So while current is less than pairs.length, we say if current is less than pairs.length, and this pair, if its start value, if it conflicts, if its start value is less than or equal to the end time, then we're going to increment current, and this really should be a while loop. And then, and really you just say something like if current's less than pairs.length, then increment the count. So you found another pair, and so current really should start off at 1. Something like this. Oh, I have to update the end time. This is wrong. TLEs, yeah. That's kind of interesting. And we're going to say end time. Yeah, increment the count and set the end time, update the end time to the pairs of current of 1. Something like this, I don't know. Okay. Let's go for it. See how we do. All right, so that's the right answer. Really awkward way of coding it though. And what this fellow did, which is interesting, is clever, is he got one less branch by starting with incrementing the count and then updating current to I don't know, does this make sense to do it this way? Wait a minute. He did something really clever. We didn't have to have as many branches, and so it was more efficient, quite a bit more efficient. How did he do this? You can actually put these at the start of the loop, right? I think. Can you do that? Try that. All right, here we are. I said I was going to try to solve as many problems as I can, but that's not what happened. It's not what ended up happening. Okay, it's a little bit better. Can you make these for loops? And then curious to see what happens when we do that. Can you do this at the end of the loop? I don't know. This could be a for loop, certainly. I know that. Right? But the question is, can you move these? Modify these. Well, you can do this first before you begin, right? And so then you don't need to do both of these here. And then you would do them after here, right? But the tricky thing is you would do them after here. However, you still need to have this if statement. And that's the tricky thing. Otherwise you get a problem. Otherwise you get a null pointer exception here when you run off the edge. Interesting. So we'll use a while loop. It's fine. Doing a little bit of extra work here, I think. But the basic idea is still there. I mean, it's still extremely efficient comparatively. All right, not as fast as it could be, but we're definitely like, I don't know, 100 times. We're way faster. We're like more than, we're almost, yeah, we're like 50 times faster. Over 50 times. We're like 52 times faster than we were before. So we're a lot faster. We're a lot faster. It's interesting. Is there a better way to do this? There might be. There might be a way to do this without sorting, which would be interesting. I think that's actually what. No, I don't think you can do better than that, because someone used a priority queue, which is like the same idea. But the problem with that though is that you're going to pop everything from the priority queue anyway, so you're better off. You're better off doing this. Simple sort. Interesting. I don't know. I don't know. Some other folks did a better job, I guess, on this, where they did somehow it was a little bit faster, and it was also less memory. I'm not really sure how you would do that exactly. I don't know. We'll try one more time, and then we'll go to the next problem. So really interesting question. Somehow some folks figured out how to do this even faster. I don't know how they did that. But yeah, the basic idea, the greedy algorithm is we're going to sort on the n times, and we're going to select of all the things that don't conflict. We're going to select the next element that has the smallest n time that also doesn't conflict with what we've already considered. And the way to prove that this works is the inductive step. You basically would consider the non-decreasing sequence defined by excuse me. You would consider so suppose you had a correct algorithm, and you consider the non-decreasing subsequence defined by applying that correct algorithm on all of the subsets of the intervals, where each subset is defined by any of the possible end times that could be considered. Any of the possible end times that could be considered. Period for any of the any subset of the intervals. So you can map out, since you can sort all those n times, and then if you apply the algorithm to those subsets defined by those n times, where the subset is all of the intervals that have an n time that's less than or equal to that particular n time, we'll call it q or something. So now you have a non-decreasing subsequence. You apply your correct algorithms to each of those, and then you could suggest, okay, given any particular n time I, consider alpha where the n time is the smallest possible n time, which could be less than or equal to I, or q sub I, we'll call it. And alpha would be like q sub alpha, where q sub alpha is less than or equal to q sub I, or just alpha is less than or equal to I, where that alpha is the smallest possible n times, such that our correct algorithm still gives us the same maximal value, we'll call it x, number of disjoint, that configuration with the same, or subset selection with the same number of x disjoint subsets, disjoint intervals. So we know that alpha exists because either is I or there's something smaller. So let's consider that. Let's consider alpha, and then we can show for some beta, q sub beta, where beta is larger than I, or we want the configuration that gives us x plus 1, right? Exactly one more disjoint interval for a given beta, and suppose that it exists, right? Because it is possible that we've already gotten we were already at the maximum for all possible intervals. But so suppose we're considering considering only the cases where there is actually consider only the cases where it is possible to add another interval from the whole set, right? Then in order to get to there may be more that may not be unique. There may be more than one beta. There may be more than one possible configuration that gives us x+1 intervals. But let's consider of those possibilities. Let's consider beta such that beta is the smallest. So of all the intervals that we could have, all the intervals that we could select to get us from x to x+1, we would want to select an interval. So these are all disjoint intervals that have starting times past alpha, that alpha end time, and all of those intervals have some ending time. We want to pick the one with the smallest ending time, which will give us beta, right? That's you could show that'll give you beta. So that implies then that if we already have if we have an algorithm that'll give us the minimum end time for a maximum for given that maximum x as described, then also if we apply the step that we just described, which is looping through all of the next possible end times that are larger than alpha, taking the smallest and also removing all of the sets that are not disjoint. So considering only the disjoint sets and removing from consideration all the sets that are not disjoint, that necessarily will give us the beta that we're looking for. So that'll give us the optimal configuration. If we include that set, it'll give us the optimal configuration for the subset of intervals that are less than or equal to that particular end time beta. That'll give us the best possible for an x+1. And so that gives us an inductive hypothesis that gives us an inductive step from x to x+1. So we're always going to have that minimum alpha for x and that minimum beta for x+1. And so at every step we have both the maximal configuration for a given end time and also the minimum end time. The interval that to select to achieve that is going to be a disjoint interval that's of all the disjoint intervals the one with the smallest end time. And at the very end, there is a point where we've actually included all of the possible intervals that we could consider. So again, that kind of refers back to I was saying that alpha is sort of the smallest possible end time where x won't change anymore. There will be a point where we actually have included all of the intervals in our set, and that's actually at the end. That'll give us the maximum value once we're done. So maximal value. Yeah, very kind of long-winded way of explaining it, but I think that's the way to explain it. I think it's true. I think it's correct. Think about that again. Yeah, it's hard to express that in English. But this is a job scheduling algorithm where we want to fit the maximum number. It's a greedy algorithm to fit the maximum number of non-overlapping intervals. Okay, fair enough. We'll remember this one for the future. Okay, all right. The proof of that is that's really complicated proof. Really hard to explain proof. But yeah, we have sort of the inductive step, and then obviously the first step we can just take the minimum end time for one, and then the inductive hypothesis will give us what we're looking for. So that's the proof. Okay, all right. Let's move on. So thank you for watching. I'm gonna start another problem.